Right, in this question, we've got a deep dive into the power law. We're looking at the distance of the Sun and the orbital period, and we know that the relationship between the distance of the Sun and the orbital period is related according to this formula P equals Sun number A times the distance from the Sun to the power of another number R. And we've got to try and find out what A and R is to get a relationship for this. And the first question asks us to use the data for Earth and Uranus to estimate the value of A and R. Now, generally on questions of this type and you want to find the equation, you put all the data into your calculator and use one of the regression methods to find the equation. But this question specifically used Earth and Uranus. So we're going to use these two data points to try and evaluate A and R. So if we do that, we know that the period for Earth is 365.2 is equal to A times by 49.6 to the power of R. And then if we got Uranus, we know that the period is 3589 is equal to A times 2872.5 to the power of R. Now, what we could do using algebra, if we divide these two equations, so here's equation 1 and here's equation 2, if we do 2 divided by 1, we get 30,589 over 365.2 will equal 2872.5 to the R over 149.6 to the power of R. So we can work out this. So what we can do is we can realize that we've got 2872.5 over 149.6 all to the power R on the right hand side. And if we go to menu 1, we can quickly work that out. 2872.5 divided by 149.6 and we get 19.2 for that. On the other side we've got what, 30.589 divided by 365.2 and we get 823.07, so on. And then we can just undo that. Now on our calculator we can use a log function. If we go into log A maths and log AB, we can do log to the base of 19.2. We'll undo this power law and we can do it of 823. So let's just do it to 823.07777656. R is equal to 2.27. And then we can put that back into one of our equations up here. So we do that to the power of 2.27, divide throughout, and we find that A comes to be approximately equal to 0.200. So we've got a formula that P is equal to 0.2 D. Just realised I made a mistake, sorry. I'm going to go back, put an extra 0 in. So I've put an extra 0 in up here. And I think if I delete that 0, press execute, it will make everything correct. Does it? Oh no, I didn't put an answer in here. So if I go up, if I put the answer in here, then it would have automatically changed everything to get me the right answer. So I get 1.49. And I was lucky because I've got the answers to check my answers, so therefore I saw that I made a mistake. What you could have done when you've done that is actually check your formula works and see that you get something that works roughly for these values. So put the values back in, check your formula works after you've worked it out, because it is quite easy to type in numbers wrong. So that's how we could use the data for Earth and Uranus to estimate the value of A and R. Create a table using natural logarithm all the numbers in the table. So we're going to do natural logarithm all of these and natural logarithm all of these. Draw a scatter plot for our table and find the line through the first and last points and use this to estimate a value for A and R. Well, I'm not going to quite do all of that. But what I am going to do though is I'm just going to call up a graph I did earlier. So here's the original data that's plotted. So you've got to see, we can see these blue points. There's our curve being plotted. Okay, and then if we take the logarithm So there's the x values, that's the log of all the x values. And if we take the log of all the y values, that's the log of all the y values. Now, the way I did this was I typed all the x values and all the y values into this table. And then I typed this formula, natural log of x1. And then it automatically worked out the logs of all of those and put it in here. Then I typed in the formula in here, natural log of y1, and put all those in here. And then, if I press this little plus sign that was here, I can go and look at these points and notice we've got a straight line. And if I put plus on here, this goes back to my original data, the blue points, and it scales it automatically for me. This Desmos.com graphing calculator is really quite useful, especially if you've got some projects to do. Now, if we do, what Desmos will also do is work out the power equation. So will your calculator will work out the power equation. And it's okay, I'm just putting an insert into the video because the first time I did this, I didn't have the log mode clicked on here. So when we use this power equation to get our line of best fit here, when we're doing this, we use the log mode. You can go and find more about log modes by clicking on the question mark here. And we find when we do that, we get our A value is exactly pretty much the same, and our R value is pretty much the same as our approximation that we did earlier. So if you choose the right 2 points, you can get a very good approximation just doing simultaneous equation, and then the regression gets you going through all the points. Now, you can also do, if you don't have that function on your calculator, then what you can do is you can take the logarithms of both sides and realize in this power equation you've got a straight line. Let's just hide that one now. And then what I did was I did a regression on that line as well. Here I did natural log of y1, m natural log of x1 plus c. So I've got my natural log of y1 is my y values that are plotted here. My natural log of x1 is my x values are plotted here. So there's my x values, there's my y values. And I've got mx plus c, so I'm going to get an equation of a line. And if I plot that mx plus c, if you use that m and that c, it'll automatically use the value 1.498 and c is minus 1.650. And you can see I get a straight line going through that. And I've now got an equation that I've got natural log of the y value equals m times natural log of the x value plus the c value. So what does that mean into my question if I work it out this way? So I've got the natural log of y is equal to 1.4988 times the natural log of x plus, in this case actually minus 1.605 and so on. Now I want to get that back into my power law. Then what I've got to do is I've got to realize I've got natural log of y equals natural log of x to the 1.4988 minus 1.605. What I'm trying to do is get natural log of this side equals natural log of this side. So I want to find out the natural log of what number will equal minus 1.65. Now if I do e, so if I now do e to the minus 1.605, I get 0.22. So therefore, I've got natural log of x to 1.4988 plus natural log of 0.200. And then I can realize I've got natural log of y equals natural log of 0.200 times by x to 1.4988. And if I take away the natural logs, I got y equals 0.20x to the 1.5988, which is my power law, which is the values. And you can see I've now got the value I've got here and I've got here. Now, let's go back to our questions. So we've used our regression line to find the value of I. I'll use the power regression. Now I'm going to use the power regression option on our calculator to find the model of the original data. So if I go to menu 2, you can see I've put the data in already. And I put the x values into list 1, put the y values into list 2, press calc, use regression, and I want to find the power regression. And we want to do y equals ax to the b. And we, sorry, I've already done this once already. So we go power. And I get that A is equal to 0.200 and B is equal to 1.4908 and the R value equals 0.999. So it's really very close to being a perfect curve. So that is how we can find our values using the power regression in our calculator. We can draw a scatter plot of original data and include this last model on the plot. I'm guessing what they wanted to do there, sorry. So we can draw, use the power regression on the calculator to find the model region, draw a scatter table, include this model on our plot. So if we go back to here and we look at this graph, this is the one they were talking about when it wants you to draw a scatter the plot and including the model on this last plot. Now we can estimate the orbital period of Ceres, a dwarf planet which is this far from the Sun, by shoving this into our formula that we found out. So we get our calculator, menu 0.200 times distance, which is 41. So as our distance from the Sun is in multiples of 10 to the 6, we didn't need that times 10 to the 6. We're just going to raise it straight to that power. Press execute, and we get 1,682 days. The key thing with these questions is actually when you're doing this data and you're trying to find the equation for the model, actually the best thing to do is to jump straight into menu 2, power up, put your values in, jump into calculations and choose the right regression that's on offer, which is the power one. And in fact, if you're doing the high level A&I course, which this video is mainly used for, you've got the log, the exponential of the power, the logistic and the sine, your sidal. These are all the models you're expected to be able to do, and they all can be done straight into your calculator.